We're going to take a look at graphing polynomials. It's Unit 2, Target 3. So by the time we get done with this, you should be able to graph a polynomial given some clues to its characteristics. Yes, I talk for a living. Thank you. So we're going to take a look. We're going to start with L. Yeah, pun intended. Anyway, leading term. Okay, so we're going to do a leading term test. Now what that does is it gives us an indication of end behavior. What is happening out at the ends as we approach negative or positive infinity. What's happening. So we need to know some terms, one of which is what's a term, thus pun intended. So we're given 2x to the fourth minus 3x cubed plus half of x squared plus 2 times x minus 4. And that's written in standard form, meaning that the exponents are in decreasing order. There's a 1 there. Okay, so descending order. And it's a sum of a bunch of monomials, mono meaning 1. Okay, so we have each individual term. And the coefficients up front, notice they're in the form of kx to the a. So each term is a monomial. A polynomial can be a power function. A power function is not always a polynomial, and we've talked about that in other sessions, but what we're interested in is the constants being called coefficients, and the first term, 2x to the fourth, is called the leading term, hopefully for obvious reason, and it's the focus of what we're going to call the leading term test. We talked about this in class, and what the leading term test does, I had you do some exercises in class, but I'm going to just summarize them here because you don't have your technology available to you, potentially. So we've got 4 possible results when we look at what's going on with the leading term. First of all, it could be positive and odd. And what that does is tells us as x approaches negative infinity, so does y. And as x approaches infinity, so does y. So I've drawn a picture there. Okay, we're looking as x approaches infinity, so as we go this way, this is positive x, then y also goes positive right here. As x approaches negative infinity, going that way, so does y. So that's what it. This is our normal x cubed parent family. We know that one. Okay, the next possibility is that it's negative and odd. And what that does is it turns it around. So as x approaches negative infinity, then y approaches infinity, and as x approaches infinity, then y approaches negative infinity. So we flip it across the y-axis. So they still go opposite directions, and that's the key issue with being an odd function, is that the end behaviors go opposite of each other. If it's positive, it has a positive slope. If it's negative, then the overall function has a negative slope. So if you look at this thing, okay, generally it has a negative slope. The third possibility is that it's positive, but now it's an even function, like x to the fourth. So as x approaches negative infinity, so does y, or I'm sorry, rewind, as x approaches negative infinity, y approaches infinity, but as x approaches infinity, y also approaches. So bottom line is they go the same direction, unlike an odd. So we know the end behavior of an even function is going to go in the same direction. So as soon as we see that, we know it's an even function. Or as soon as we see that it's an even function, we know what the end behavior does. And of course, the fourth possibility is that it's negative and even, which just flips it across x, and like x squared, negative x squared. So again, the end behavior goes the same direction, but now it goes in the negative, or towards negative infinity, as we see here. Basically, what the leading term test does for us is it tells us the end behavior. So it dominates the behavior of the entire function. So even though you might have a function that does other things, like in the middle of this thing, we know what the end behavior is because we have a leading term test that will tell us, okay, this is our end behavior. This is an even, so we know that. Now that brings us to the second part of this. We now know the end behavior, so we can look at any polynomial and know the end behavior. What we want to look at is, okay, where are the zeros and the local extrema? So what I've done is I've drawn several, and these are all odd functions, and the extrema are the purple, and the zeros are the red. So the zeros, where it crosses the x-axis, so this thing goes like this, where it crosses the x is a 0, and where it crosses, or where it's locally a maximum or a minimum, then we're looking at extrema. So what this allows us to do then is fill in some of that between the end behavior. What does it do as it approaches 0 and so on. Now, we're going to begin this. Okay, we can study lots of these. In fact, we did this in class a little bit with both odd and even. And there's a pattern. If we look at enough of them, there's a pattern. So given some function of degree n, then it has at most n minus 1 local extrema. So if it's, for example, x cubed, it can have at most 2 local extrema. If it's x to the 5th, it can have 4 local extrema, and so on. And then it can also have n zeros. So if it's x cubed, it can have at most 3 zeros, but it doesn't have to have more than 1. So we got to be careful with the n equals 3. It can have at most 3 zeros, but it can have 1, it can have 2, or it could have 3. What it can't have is 4. So now we can predict the end behavior given any function and possible zeros. And of course, we want to know exactly where those zeros are. I mean, that's the whole idea of solving functions in the first place is, okay, where are they 0? We need those identifiable points on the graph. All right? We need to be able to fill in the details. So we can say, for example, all right, we've got an x to the 5th, so we can have 5 zeros. Well, where are they? Okay, well, we need a little bit more detail. So we've got two options to do that. One, of course, is the technology. Now, when you're given a function on the technology, you want to zoom until you see the proper behavior. You could actually enter something on your calculator and it will not show you the proper end behavior. And so if that happens, then you need to zoom out until you know, okay, that's the proper end behavior. As soon as you do that, okay, let's, all right. Apparently I've already drawn this out. I was going to draw another picture, but obviously I've already done that. So here's what we got. We know it's a cubic, x cubed. So we know, generally speaking, the end behavior should be opposite. It's positive, so we should have something like that. But we could actually enter in, and your technology, the whole screen shows you something that does this. Okay, we know that that's not the end behavior that we need. This side might be okay, but we need something going this way. And so we know that that's not correct yet, so we got to zoom out until we can see the proper end behavior. Then at that point, you can focus on what happens around 0, or what happens around the origin, or what happens as it crosses the x-axis. So you try to find the details. Now on the cache unit, I don't know about all of the others, but this is your focus. But on the cache unit, you're able to analyze this graph and find the zeros. So you know, we've been through that. We've been down that road. So using the technology allows you to find the local extrema and zeros, but it depends on the flavor of your technology. Our cache units that we use in class, yes, we can do any of that and a whole bunch of other stuff that we haven't even talked about yet. If you have an 84 or something, I don't know. I don't know how to run those things, so you're on your own there. You might be able to do it. I don't know. That's up to you. Now, in addition to the technology, let's say, for example, you don't have the technology available, we can use your math algebra skills that you all have, of course, and find the zeros. I mean, that's what you did before in Algebra 2 and yada, yada, yada. Okay, so let's do a little algebra here. We're given x cubed minus x squared minus 6x is equal to 0. Okay, first thing we do is factor out an x. I even color-coded this. Look at that. So we factor out the x. Okay, that's this guy right here. So if we do x times x squared, we get x cubed. X times negative x is negative x squared. Okay, you get it. I know you get it. The next part is factoring the quadratic. That's where many of you, okay, if you can do factor fish or whatever that is, then you can do that. I don't know how to do that. Okay, for me, I just got to figure it out. Old school. Never heard of factor fish, but anyway, I've heard of salmon and all kinds. But if I can't catch it, I'm not interested. So, x squared minus x minus 6. I know in order to factor the 6, you're looking at 1 and 6, 2 and 3. I've got a negative 1x, so for me, it's easier to do that than doing some fishing. So anyway, I know I got a negative 3 and a positive 2, and so I've got that factored out. Now, what that translates to, however, is the most important part. So we've got x times x, or rewind, x times the quantity x minus 3 times the quantity x plus 2 equals 0. So any one of those factors could be 0. So x is 0, or x minus 3 equals 0, so x is 3, and x plus 2 is 0, so x is minus 2. So we now know that our graph, we know the end behavior, and we know it has zeros, and it crosses the x-axis at the points 0, 0, -2 and 0, and 3, 0. So when we're sketching this thing, we can take our graph, and we know it crosses the x-axis at -2. So let's take a look here a little more closely. I'm changing color as I speak. Okay, so we know goes through at 0, 0. First of all, we know the end behavior. Okay, so we know it has to go this way. The end behavior over here has to go that way. And over here, it has to go that way. Well, if we're going to go through the point 0, 0, and we start, and we're going that way, and we're going that way, then the only way that's going to happen is if this thing has to turn around up here, and it's going to go through 0, 0, but it's got to be going this way. We also know then it goes through -2, 0, and so that's pretty easy. We've got this part of the graph, so it goes through -2. We don't know exactly what happens here, but we know it turns around, so it can go through 0, 0. Then, because our end behavior is this way, we know, well, it's got to turn around, and it's got to go through 3 right there. And so we've got a pretty good sketch of what that graph is. We're missing some detail in these two areas, but that's okay. At least we have a general idea what it's like, and of course we can use technology, go back and fill in some of those missing pieces. Alright, next piece of the puzzle is, okay, what if we have like x to the 5th and things like that, and where are all these zeros coming from? And so we got to take a look at this, and this is, it's easy to determine it in what the multiplicity is. It's a little bit less intuitive to understand how that happens, but we'll define it and we'll use it and go from there, and we'll fill in the details a little later. So if we're given a term such as x minus 2 squared, what that means is that we have x minus 2 times x minus 2, so that 0 occurs twice. All right, so it has a multiplicity. When we talk about the multiplicity, it has a multiplicity of 2. And so it's pretty easy to figure out where the 2 comes from, I hope. If we have x minus 2 cubed, that has a multiplicity of, wait for it, yes, indeed, 3. X minus 2 to the 4th has multiplicity of 4, and hopefully you can see a pattern. Alright, one more thing about this. If we look, and particularly using our technology, and we look at an examination of the odd versus even multiplicity. So this is odd still, this is even still. All right, so odd multiplicity. What it does is, when it's an odd multiplicity, we get another pattern, and that is the odds are going to cross the x-axis, and the evens are going to touch the x-axis. So it gives us a 0, but it doesn't change the sign of the function. So when it's odd, the function values change. So they go from like positive to negative or negative to positive, okay, whichever way they're going. But the even touch the axis, but the function value sign doesn't change. So if it's below the x-axis, the function value is still going to all be negative. If it's above, it's going to be positive. Now, all of that is consistent with our parent function behavior. Okay, odd, x cubed, crosses the x-axis. X squared, x to the fourth, so on, do not cross the x-axis, and so it's actually consistent with parent function behavior.